And that's when I realized it wasn't my dog at all. Oh, man. You guys are so funny. All right. So calorimetry, we talked about last week, calorimetry experiments, and we said the example that we did last time and what we just had on the quiz, shouldn't say that. No, I can say that because the class would have already had the quiz. Okay. Was that, in that calorimetry experiment, we didn't take the Q of the calorimeter into account, right? Sometimes that's negligible and you don't have to worry about that. But if you're going to have the most accurate answer possible, you do need to take the calorimeter into account. So we're going to talk about that now. In reality, it does have an effect on your calculation, so it is more accurate to do that. But when you look at the chart on page 392 in the book, which has some specific heat capacities of various substances, those are pretty simple substances. The composition of a calorimeter is more complex, so it's harder to use a chart like this. And so when we talk about one thing about these substances here, the units for that substance, the unit is joules per gram degrees Celsius. All right, and this gram value here tells us that this particular value is for a specific mass. So when we talk about specific heat capacity, we're talking about a specific mass of that substance, okay? And so since a calorimeter is so complex, you normally don't, it's not specific heat capacity, but you look at the heat capacity. And because it doesn't refer to a specific mass, it's missing that gram unit. So the units are different. This is specific heat capacity here. And this is just the heat capacity unit. So you can just by looking at the unit figure out if you're talking about a specific heat capacity or you're just talking about heat capacity. And so anyway, it tells us how the entire object absorbs or releases heat. All right. So when we're figuring out, let's see, where are we? I'm here. Sorry. So the Q for calculating the heat absorbed or released by the calorimeter, the Q that you use is capital C times change in T. All right, and so this is a capital C, and it's not the specific heat capacity, but it's the heat capacity. And that's the equation that we'll use whenever we're talking about the calorimeter. Again, if you're given that value and it contains a unit for mass, then you know it's a specific heat capacity. If it doesn't contain a unit for mass, then you know it's just the heat capacity. So it looks just like the formula that we had before, but it's missing what? The mass, right? It's missing the mass. So let's do an example and calculate that on page 401. And page 401 says that we have a 250 gram sample of an unknown metal that's heated to 350 degrees Celsius. So mass of an object equals 250 grams. It's heated to 350 degrees Celsius, so the TI for the object is 350 degrees Celsius. It is then dropped into to a calorimeter that contains 1,500 grams of water, so the mass of the liquid is 1,500 grams. It's initially at a temperature of 24.2. The initial temperature of the liquid is 24.2 degrees Celsius. The water reaches a maximum temperature of 31.2 degrees Celsius, so T final for the liquid is 31.2 degrees Celsius. If the heat capacity of the calorimeter is, so they give us that, so capital C here for the calorimeter is 1,410 joules per degree C. So we know we're talking about heat capacity, not the specific heat capacity. So they ask us, what is the specific heat capacity, the C of the metal? And so in our formula that we have, it's the C of the object, right? That's what we're trying to figure out. So this is actually very similar to the problem that we just did on the quiz, right? Except this time, we're given the C for the calorimeter, so we have to take that into account. All right? So let's see if we can tackle this problem. So the change in T, we can do just like we did before. We can first calculate the energy or the heat for the liquid. So that's going to be, we've got to first calculate the change in T. So the liquid went from a final temperature of 31.2 degrees Celsius. That's what it ended up as. The initial temperature was 24.2 degrees Celsius. So our change in T for the liquid is 7 degrees Celsius. So then we can calculate the Q for the liquid to be the mass of the liquid, which was 1,500. Remember, this is M times C times change in T. So it's 1,500 grams. What's the C for our liquid? 4.184 joules per grams degrees C times the change in temperature, which we just calculated to be 7 degrees Celsius. So the Q for our liquid is 44,000 joules. Now in our last problem, we could calculate the Q for the object as soon as we found the Q for the liquid because we didn't have to take the calorimeter into account. But this time we do have to take the calorimeter into account. And so we have to use that equation over there and say the Q for the calorimeter is going to equal capital C times change in T. And they gave us capital C as 1,410 joules per degree C. And what's the change in temperature for the calorimeter? How do we calculate that? Can we calculate that?
We have to use the equation where it's change in temperature equals the T initial minus T final. T final minus T initial.
Right, T final minus T initial. But do we have that? Have they given us that? How many people say yes?
But isn't it the same as the liquid?
What's that?
I said, isn't it the same as the liquid?
That's right. Right? The liquid and the calorimeter, always think of the temperature changes in those as being the same. Right? Whatever the initial temperature of the liquid is, that's the initial temperature of the calorimeter. If I were to give you the initial temperature of the calorimeter instead of the liquid, you would know what the initial temperature was of the liquid, right? So let's see. There's some names I haven't been writing down. I'm sorry. I was counting on ringing the trash can, and I didn't think I was going to worry about writing down names today. So I know you just gave me the 4.184, and Joey gave me the initial temperature of the calorimeter. And I'm sorry, there were people yelling out answers when I was working the problem on the quiz, but I was just so confident that I was going to ring that, let you down. So you don't have to answer some more questions. Say something else that's mind-blowing. All right, so it's going to be the same, right? So the point is this value is going to be the same for the calorimeter. The change in T is 7 degrees Celsius, just like we calculated before. So our final Q for the calorimeter then is going to be 9,900 joules. And these are rounded to nice even numbers because they're taking, as he's coming up with these values, he's using the correct number of significant figures. You're not going to get exactly that if you punch it in your calculator. So now I have enough information to figure out what the Q of the object is, right? Does everybody agree with that? Yeah? You're like, you said it, so yeah, we're going to shake our head whether we really have any idea what you were just talking about or not. But we do. We have enough information because we know that negative Q of the object equals the Q of the liquid plus the Q of the calorimeter, which is 44,000 joules plus 9,900 joules. So that gives us 54,000 joules. Again, rounding to the correct significant figures.
I thought it was 53.
Well, this is almost 10,000, plus 44,000 would be 54,000, so yeah, he's rounding, like I said, he's rounding to just use two significant figures. So that means the Q of the object is the negative of that. Negative 54,000 joules. All right, so we're almost there. Now we just have to do the same exact thing that we did on the quiz and to calculate the specific heat capacity of the object. And so we solve for C in this equation right here. If Q equals mc change in T, then C equals Q over m change in T. And the Q of our object is what we just calculated, negative 54,000 joules, divided by the mass of our object was given at the beginning to be 250 grams. The change in temperature for the object, T final for the object is what? Do we know that?
Oh, it's the same as all the other ones. So
Yeah, in a calorimetry experiment, the final temperature is the same for everything, right? The object goes in hot and it cools down. When it goes in hot, it heats up the liquid and the calorimeter. And so the temperature raises on those and they meet an area in the middle where the temperature becomes the same, right? And so the final temperature is the same. So it's going to be 31.2 degrees Celsius minus whatever the initial temperature was for the object, which they gave us to be 350 degrees Celsius. So we punch all that into our calculator, making sure we do the stuff inside the parentheses here, the subtraction first. The change in T there is negative 318.8 degrees Celsius. And then when we punch all that in, we get 0.68 joules per grams degrees C. So that was basically, like I said, the same exact problem we just did on the test, except this time we were able to include the value for the calorimeter, the heat, or the energy as it was related to the calorimeter. Any questions about that problem? So we've really seen almost the same exact problem twice, right? We've worked through those, so you guys should ace this on the test, right? Any questions? Anything that you're still confused about with that? Really, this is a pretty simple chapter, but you just have to make sure that you're plugging in the right value in the right places, right? You can't get confused when you're figuring out the Q. You know, when you're talking about the Q of the liquid, make sure you're plugging in values for the liquid. Talking about the Q of the object, make sure you're using the values that are specific to the object. But the equations that we have, Q equals MC change in T, and then we just learned this new one, Q capital C times change in T. We know the Q of the object when you're dealing with a calorimetry experiment is the negative Q of the object is Q of the liquid plus the Q of the calorimeter. And are there any other equations we've learned so far? I don't think so. The rest of the stuff was just kind of definitions. So I'm going to give you a few more definitions at the end of this chapter. And we're going to learn one more Q that we can calculate. But not a lot as far as the math goes. And none of it's really particularly complicated. Huh?
Isn't the change in temperature also?
Change in temperature, yeah, you could write that down. Change in T equals change in T final. Yeah, you do want to make sure you get those in the right order, right? Change in T initial. So, yeah, good point. Make sure you know that. All right. Okay, so let's move on to talk about latent heat. Latent heat. Kind of hard for me to say. I have to be very deliberate and slow when I say latent heat. Pronounce those T's very clearly. All right, what is latent heat? Whenever in chapter 6 we learned that during a phase change, the temperature of the substance doesn't change. So we saw a graph that, I think there's a graph in the book like this, but it sort of looks like this, where this is like 0 degrees Celsius if we're talking about water. And so you have water that heats up and then comes over here, it heats up again, it levels off here, and then the temperature increases. And so like right here, this is 100 degrees Celsius. So this is our temperature side of the graph, and see if there's still enough juice in here. You know what? Maybe let's just see. Not really. I was like, maybe the reason I couldn't throw it away is because there was a little bit of juice left in it. It's pretty much gone. That's the access on our. I'm trying to identify that that's the. This was at least writing a little bit before. Probably slamming it into the side of the thing earlier wasn't helping much. But so as it increases here, and then levels off here, and then increases here, and levels off there, and increases here. What's happening here is that the water is going from the solid phase to the liquid phase, so it's melting, right? The solid water, the ice, is melting. Right here, it's transitioning from the liquid phase to the gas phase. So it's what we call vaporization. So you've got melting taking place here, and you've got vaporizing taking place here. All right. And so this is time along this line here. So as time is going along, you kind of have this period where it levels off and temperature doesn't change. Then over time it goes up, and then it levels off again as it's converted to a gas, and then the temperature will continue to increase. The stuff that we're calculating, you notice all of the Q's that we have here. These two here, they both have something in common, right? What's the one thing in common as far as this side of the equation goes? They change in temperature, right? But what is not happening right here during this process? There's no change in temperature, right? So we can't use these Q equations to figure out what's happening with energy in these phases. And so what we refer to this portion of the graph as is what we call latent heat. And so latent heat, right? Because remember, that's what Q represents, the heat or the energy. Heat's just a form of energy. Latent heat, we define, another definition I want you to know, it's the amount of heat absorbed or released by a substance during a phase change. So even though the temperature's leveled off at that point, energy exchange is still taking place. Absorption or release, or the release of energy is still taking place. And we call that latent heat, and it's represented by a capital L, the letter L, uppercase L. All right. Now, this right here, this portion we refer to as LF, which is the latent heat of fusion. I did it again in last class. I wrote my U like it was an A, so they were confused about what I've written on there. The latent heat of fusion. And that is the energy to go from a solid to liquid. And then this portion here, we refer to this as LV. It's the latent heat of vaporization. And that's the energy to go from liquid to gas. What's the energy during that phase change? And so the formula for this latent heat, like I said, there's no change in temperature, so we wouldn't expect it to have change in temperature in it like the other equations do. This this equation just looks like this. It's just the mass of the substance times the latent heat of that substance. And depending on where we are on this graph here, you'll determine whether or not you're going to use the latent heat of fusion or the latent heat of vaporization. So for ice to melt, is it going to be absorbing energy or releasing energy? What do you think? I think it's releasing energy. Huh? Absorbing? Just think about it this way. For ice to melt, it's gotta have, the heat has to go up or down? Up, right? It's got to get warmer. The temperature's going to change and get warmer. So it's actually going to have to absorb that. It's going to have to take in energy in order to heat up and melt. But the opposite happens when ice goes from liquid to its solid state. When it freezes, it actually it's going to give off heat, right? It has to get rid of energy in order for it to cool down to the point of freezing. And so what actually it's interesting, whenever water freezes, it actually makes the environment around it warmer. Not by a lot, right? It's like as it's freezing, we don't all of a sudden get warm. But if you measure that, you will in fact see that the environment around the water as it freezes gets warmer because the water is giving off energy. It's releasing energy in order to freeze. All right, so that's kind of cool. So let's do an example using our latent heat formula, and it's on page 404. Example 13.4 says water has a latent heat of fusion. So they give us the LF for water to be 334 joules per gram. And a latent heat of vaporization, the LV, they give us to be 2,260 joules per gram. If 150 grams of water freeze, they tell us that the mass here is 150 grams. So much water we have. How much energy is involved in the phase transition? So this is water freezing. This is this portion of our curve, right? Of our graph. It's down here. It's going from liquid to a solid state down here. And so the L, so the equation we're going to use is this Q equals mL. But which L am I using? Am I using LF or LV? As it goes from liquid to solid. LF. It's always, if it's down here on this part of the curve, it's always going to be LF. Whether it's going from a solid to a liquid or a liquid to a solid. Okay, it's always LF. When you think of vaporization, you think of vapor, and that makes you think of gas, right? And so if it's something that's going to go, if it's going from liquid to gas or the reverse of that, then you're going to use LV, all right? But if it's solid to liquid or vice versa, you're going to use LF. Does that make sense to everybody? So use the LF value. So our equation then for what they're asking is going to be M times LF. So we just plug those values in, 150 degrees times LF, which is 334 joules per grams. So we get joules per gram, I should say, 50,100 joules. That's our answer. And the second part of the question was, is the energy absorbed or released? So it went from, in this problem, it froze. It went from liquid to its solid state. So if it's going to, in that case, we're thinking of it getting colder. So if it's getting colder, it doesn't want to take energy in. It's got to get rid of energy, right? Remember, like I said, when it freezes, it actually gives off energy and heats up the environment around it a little bit. So is this energy absorbed or released? This is the energy that is released. Does that make sense? You guys see how you need to think about that? All right. So now, having learned all of this stuff, we're going to put all of it together in one big problem, and I could kind of give you this one big problem on the test, and we would just be done, right? This would be the whole thing. That'd be awesome. So if you miss something, that we count like 20 points, and you could, miss one little part, and you make like a 35 on the test. That doesn't sound fun. So let's not do that. But we could, because it's going to kind of test everything. But we are going to add this new equation to our arsenal over here. M times L, right? So we've got 3 different equations that we can use to calculate energy or heat for a particular object or substance. But now what this gives us the ability to do is do a full energy analysis of this process here. Like when we see a substance go from its solid state all the way to its gas phase. All right, so that's what we're going to do. That's what this last problem is asking us. So I'm going to erase some of this so that we can, we're still going to use the graph so we can identify which region that we're looking at. But I'm going to make sure we label this again. This is the LF, and this is the LV. All right. So this next problem says this. We have an ice cube that's 125 grams. So the mass of our ice cube is 125 grams. It's at a temperature of negative 8.7 degrees. So the T initial, so this is the mass of the ice. The T initial for the ice is negative 8.7 degrees Celsius. At 1 atm, at normal atmospheric pressure, how much energy would it take to turn all the water in that ice to vapor? And so they give us a few other values that they kind of hinting that we may need for this problem. So the C of ice is 2.093 joules per grams degrees C. They give us the latent heat of fusion to be 334 joules per gram. They give us the latent heat of vaporization to be 2260 joules per gram. And there's one other thing we're going to need for this problem, and that is the C for liquid water. And we have memorized that, and we know that to be what? 4.184 what?
Joules over grams.
Right? All right. So, in order to figure out what the how much energy would it take to go all the way from an ice cube to vapor, this is what we've got to do as far as our graph here is concerned. All right. We're going to first calculate so our point down here where we started at was negative 8.7 degrees Celsius. All right. So first we're going to have to calculate the amount of energy from here to here. All right, so the Q for that first. Then we're going to calculate this Q that runs from here to here during this flat region. All right, and then we're going to calculate the Q that runs from here to here. There's another Q there, and then finally there's a Q that goes from here to here. And then once we get that, once we get through the latent heat that's involved with this vaporization, at that point it's all turned to gas, and so we don't care about anything beyond that, because we're just wanting to know how much energy is required for this ice to go from a temperature of negative 8.7 degrees all the way up here to where it's all turned into gas. All right. So you guys see what we're trying to do? Trying to figure out the Q for each of these stages as this process is taking place. All right. So let's start with the first one. The first Q is it's not the latent heat. So we're going to go back and use and it's not the Q for the calorimeter. In fact, that's the only time we're going to need this equation here is when we're dealing with the calorimeter and we're trying to calculate the Q for the calorimeter itself. So we don't really have to worry about this equation for this problem. So we're using this, mass times C times change in T. What is our change in T for this portion of our graph? Change in T for this portion is the T final. What is T final for this portion here? 0 degrees, right? Minus T initial, and T initial they gave us to be negative 8.7. Does everybody see that? So minus a negative 8.7 degrees C. So our change in T for this is going to be a positive 8.7 degrees C. So when we plug in all of our values, so we're going to call this Q1. This will be Q1, Q2, Q3, Q4. Q1 is going to be 125 grams. In all of these problems, because we're dealing with the same substance, it's going to be 125 grams for the mass every time, right? Because we're watching how the water is changing as it goes between the different phases. C for Q1 is going to be what? It's going to be the C for ice, right? Because right now it's in its solid phase, so it's going to be 2.093 joules per grams degrees C times the change in T, which we calculated to be 8.7 degrees C. So the value for the energy exchanged during this portion of the process is 2,300 joules. 2,300 joules. So I'm going to underline this each time we calculate one of the Q's. All right? So I'm going to label these as equation 1, equation 2, and equation 3 as far as our Q equations go. So that tells us Q1. What about Q2? Which equation over here am I going to use for Q2? The third one, right? Because it's the one that doesn't contain the change in temperature. And the temperature is not changing right there, right? So for Q2, we're going to use the equation mass times L. So the only thing we have to figure out for Q2 is if we're talking about the latent heat of fusion or the latent heat of vaporization, if we're talking about this area down here. Of what? Fusion, right? So we just plug those values in. 125 grams times, they gave us LF to be 334 joules per gram, and we get a final answer of 41,800 joules. Is anybody lost at this point? Is that straightforward enough for you? You see how we're breaking it down and how we have to analyze each one? Again, these equations are really, really simple. It's just understanding how you piece all of it together as we're looking at the different chunks of the graph. Yes?
I'm understanding it so far, but what I'm confused about is why do we have like 4 Q's on the graph? Like I'm confused at what we're trying to go for exactly.
Right. Okay. Well, when we first started looking at heat or the energy that we refer to as heat, this was the first equation that we learned, right? And so we had some substance, and we'd have a change in temperature for that substance. And if we said, for example, gold was our substance, well, we had a little chart, and we could look up what the C was for gold, right? And they would tell us in the problem what the mass was of that gold, and then what the change in temperature was for it. And so we could figure out this Q value. But this Q value here was always dependent on a temperature change, right? This is the same kind of thing, but what we did before was we just learned how to calculate this sort of stuff along these regions of the graph. Why? Because along these regions of the graph, there's a temperature change, right? So I could have given you a problem and said, we have water. We have liquid water that goes from 0 degrees Celsius to 100 degrees Celsius. tell me the energy involved in that process. And you would put in what the mass of the water was, the specific heat that we learned to be 4.184, and we'd say the change in temperature was 100 degrees. And that would have been what was happening with water along that portion of the graph, right?
So this isn't one problem itself. This is like...
So several pieces put together. So we learned that first, where the temperature changes, and then we said, but there's this kind of special process going on whenever a substance changes phases. And during a phase change, there is no change in temperature. As a substance is going from one phase to the next, whether it's going from a solid to a liquid or from a liquid to a gas, there's a leveling off of the temperature, and during that period of time, the temperature doesn't change. And since there's no temperature change, then this value here would be 0, and if we were to use this equation, we'd say there's no heat involved. There's no heat or no energy involved in that. That's actually not true. There is energy, and that's what we call latent heat. And so for this flat part of the curve here, when the phase change is taking place, we learned how to calculate that latent heat using this equation. Okay? So what we're doing is we're putting all of that together now in one problem. We're saying, here was the first Q that we learned how to calculate. This was because this is the flat region, this is the second type of Q we learned how to calculate. And then as it continues to heat up again, we're back to learning about we're back to using the first type of Q that we learned how to calculate. And then there's another flat portion here, so we're back to using latent heat again, which we just learned about today. So we basically have to calculate all 4 of those and add it together to see what the total energy exchange was like. Does that make sense?
Sort of,
They're
yes.
like all the same.
So it's all of those pieces kind of put together, and that's why I said I could give you this problem, and really I could test you on all of the stuff that we've learned with just this one type of problem, because, except for maybe this portion, right? I'd still have to do a calorimetry experiment to get you to use this equation here, but most of the stuff is going to kind of be contained in this process. Yes?
And whenever it's flat, that means it's not a change in temperature, or is it?
There's no change in temperature.
Okay.
Right, yeah, because see, this is our temperature scale over here, and since this is flat, through this is our timeline, right? So this is time down here. So as time's going along, for this period here, it doesn't change temperature, it stays at 100 degrees Celsius. And that's where the latent heat is taking place, is in there, okay? Good question. Anything else? So talking through that and explaining that one more time, did that maybe click a little better for some of the rest of you? Why we've got all these different Qs? And the reason we've got different Qs, like even though this is, you're going to use the same type of equation between here for this portion and for this portion, like we're about to calculate that, Q3. The reason we call it Q3 is because it's not going to be an exact same equation because the temperature change is different here than it is down here, right? The change in T is going to be different for this portion. Also, what else is going to be different for this portion here? Because remember, we're back to using this equation here because we do have a change in T, so that's the equation that we're going to use. Mass hasn't changed. Mass is still 125 grams. We still have the same amount of water. But what about the C? What C do we use for this portion of the graph?
Oh, for free. No.
We're going to have to use the liquid one. We use this one for the last portion, but now it's not a solid anymore. It's liquid water, so we're going to have to use that C for this portion of the graph. Does that make sense to everybody? So here, our C is going to be 4.184 joules per grams degree C. And what about the temperature change here? For this portion of the graph, it went from negative 8.7 to 0 degrees Celsius. And so we had a temperature change of 8.7 degrees Celsius. But for this portion, this change in T, the final temperature is 100 degrees Celsius. The initial temperature was 0 degrees Celsius. So for this portion, the change in temperature is 100 degrees Celsius. Does that make sense? Yes? No? Kind of, sort of? Kind of? Because we're just looking at this portion of the graph here. Just that region there. Alright? And the only thing that we have to remember for this portion of the graph here is that it's liquid water, so we're going to use that C, and the temperature change is from here to here, the difference between 100 degrees and 0 degrees. Alright? So this Q comes out to be, when we punch it in, they've given it in scientific notation. I'm not going to do that. I'm going to write it out like this. That's what you're going to see in your calculator. They're just using scientific notation to maintain the correct number of significant figures. So we have one more Q, Q4. Is this going to be latent heat that we're talking about in this one, or is it the heat that we learned about at the beginning of the chapter?
Later heat.
It's latent heat because, again, there's no temperature change during this portion here. So it's going to be mass times, but it's not the latent heat of fusion. It's not down here in this region of the graph. It's the latent heat of vaporization because it's this portion of the graph, right? So it's just the mass of the water. Again, the mass doesn't change throughout this process. And the LV is this value here, 2,260 joules per gram. So that gives us a final, I forgot to underline that, that gives us a final value of 283,000 joules. Like I said, they asked us what the problem asked us for is what's the total energy? How much energy does it take to turn all of this water in the ice cube to vapor? So what's the total energy that was used over this entire portion of the graph here, up to this point, right? We don't care beyond that point because once it hits this point here, it's all turned to vapor. And that's all they asked us. How much energy did it take to turn the ice cube into vapor? So to get the total Q, we're going to have to add up all the Q's that we just figured, that we just calculated. So it's 2,300 plus 41,800 plus 52,300 plus 283,000. So our final answer is 379,000. That is the final answer to our problem. If you punched all that in and you got a more precise answer, technically because of what we've learned with significant figures and precision and all, this is the answer that you should give, but like I said, I don't want you stressing over that, right? I just want to make sure that you can use these equations and perform these calculations. Any questions overall? Now that we're through yes?
So I noticed that the higher up we go on the graph, the more heat or the more energy it takes.
Right.
Is that true for like every time you go up in temperature, there's more?
You know, I don't know off the top of my head. I don't know if that's true. I mean, what I do know, you know, some of the things that contributed to these numbers being higher here is that we know for water that the specific heat capacity in its solid form is less than the specific heat capacity in its liquid form, and so I need to look that up. If that's true for all substances, then yeah, I would say that you would always kind of see this pattern of the numbers increasing, you know. But off the top of my head, I'm not sure. Is there another reason why this would, like with LV and LF, again, we see a higher number for LF and LV. So is that kind of true across the board? I'd have to look that up. That's a good question. Or if somebody wants to tell me that, how about that? I like that. How about the first one that figures it out and sends me an email, then I can give you some extra credit for that. Extra credit opportunity? I'm going to look it up too, but if somebody can tell me what the answer is, will these values always get higher as you go along this graph here? Well, is there more energy required always, regardless of the substance, to go? I would say for water, yes, this is always true, right? Because we see the difference between the LF and the LV and the difference in the specific heat capacities. But is that true for every substance? Will these numbers always get bigger as you go along this curve? Now, I will say this, and this is kind of important. You know, this number actually, I can tell you for sure that it won't always be the case. Because even in this problem, what if the water hadn't started out at negative 8.7 degrees Celsius? What if it started off much, much colder than that, right? What if it had started at negative 100 degrees Celsius? Well, this number here is going to be much bigger now. So this number here is going to be much bigger. So depending on our starting point, we know for sure that this portion here could have a larger value. Because of the freezing point and the boiling point of water, this value here is going to be, you know, that's why it's 100-degree difference. But what about a substance that has a wider range, you know what I'm saying, between, or has a smaller range? That's definitely going to affect these numbers as well. So I don't know. I don't know if there's a straightforward, you know, one-size-fits-all answer to that question. I just have to look it up and see. But if somebody finds something, some useful information on it and wants to send it to me, I'll give you some extra credit. All right? Any other questions about the problem as a whole? All right, I just got to give you a couple of definitions and we'll be done today. All right? Like I said, that's basically the extent of the mathematical part of this particular chapter. So, if you understand how to calculate latent heat, and you can do a problem like that where we kind of go from, the solid phase all the way up to the gas phase, or I could give you a problem that asks the reverse, right? What if it went down all the way from the gas phase down to the solid phase? You could calculate that as well. All right, so we've been looking though primarily at heat as it relates to physical changes, right? Phase changes. That's a physical change when you go from solid, when water goes from a solid to a liquid or a liquid to a gas. But there's also heat in chemical reactions. So what about heat and chemical reactions? Let's talk about something called exothermic reactions and endothermic reactions. So an exothermic reaction is a chemical reaction that, and I'm not going to fill this in yet, that blank energy. Endothermic reactions have the same exact, I guess I shouldn't say, there should be no S there because I said a chemical reaction. So an exothermic versus an endothermic reaction is a chemical reaction that blank energy. Does anybody know what words I should put where the blank is there?
Exothermic, I'm pretty sure, is where it releases energy, and the endothermic is where it absorbs energy.
That's right. So this releases, and this absorbs. So in a chemical reaction, what are some examples of that? Have you guys ever used, I guess they're still called this, hot hands? Those little plastic things you can put inside your gloves or whatever, and you crush it up, and all of a sudden it gets hot. What's happening? It's a chemical reaction that's an exothermic reaction. You're mixing those chemicals together, and it produces heat. It gives off heat. Also, if you've ever had to go to the hospital and, you got a big swollen place or whatever, and they're putting ice on it, they've got those ice packs in there, and the same kind of thing. They crush those ice packs, they break them, and mix everything up together. And so they're taking chemicals and mixing them together, and it's an endothermic reaction is performed, and it absorbs heat. And so therefore, it absorbs energy and it gets colder. So those are two examples of, that's an example of each of those types of reaction. Those types of reactions. So he asked a question here at the end of the chapter.
Mr. Walker?
Yes.
Yes. I was just asking if those chemical reactions would be an example of something losing temperature without losing energy. Because the two chemicals get mixed together and lose.
Well, there is a change in energy, and that kind of goes to this next question, because he asked this question in the book: where does the energy in an exothermic reaction come from, so that it can be released during the reaction? So how do we need to think about that energy? And it kind of goes along with your question that you had. Where does the energy come from if it's going to be producing energy as those two chemicals come together? And so he makes the note that before, and I want you to memorize these. I may just ask you on a test to give me the definition of those. There's two types of energy that we need to consider before we can answer that question, and we're not going to really answer that question until the next chapter. But there's kinetic energy. You've probably learned this from physical science. We probably discussed this. Energy that is in motion. So when you hear kinetic, think of motion. If there's motion involved, then it's kinetic energy. Potential energy is energy that is stored. So, we kind of use the example of a boulder at the top of a hill, right? And that boulder's sitting up there, and it's not moving. There's no motion, so it's not kinetic energy that we're talking about with that boulder. But if I push on that boulder, all of a sudden now, there's a whole bunch of energy as that boulder goes rolling down the hill, right? And flattens your poor friend that happened to be there with you, right? It's those things happen. So watch out for rolling boulders downhill. This is really the point to that story. But there was a lot of potential energy. There was the potential for that boulder to do a lot of damage as it sat at the top of the hill, but because it wasn't moving, there was no kinetic energy that was being displayed, right? So potential energy, it's stored up energy. There's the potential for that energy being released. Kinetic energy is when the motion takes place and that energy is actually being released. All right? And so we'll discuss that in the next chapter. But that's it for this chapter.